Bismillahirrahmanirrahim. And today lecture of the thermodynamics course having course code of PHY331. I would like to discuss the hydrostatic systems and mathematical theorems regarding the hydrostatic systems and some from the differential equations. So actually the learning objective from this lecture is to understand the hydrostatic system. We have different type of hydrostatic systems, and finally the mathematical description or the mathematical theorems from the differential calculus. The first things we need to know is the hydrostatic systems. It is actually an isotropic systems having constant volume and constant composition, that is exerting a uniform hydrostatic pressure in the absence of gravitational, electric and magnetic effects. So this is called as a particular hydrostatic systems. Based on the composition of the substance, it is divided into three categories or three types. The first one is the pure substance. If you consider a substance that has single chemical, that is actually a single chemical compound in the form of solids, liquid or gas, then it is called as a pure substance. Or it may be a mixture of two pure substance, or it may be a mixture of three. And the second one is the homogeneous mixture. In case of homogeneous mixture, we have different compounds such as a mixture of inert gases, or a mixture of chemically active gases, or a mixture of liquids or a solution. And the third case is the heterogeneous mixture. It is actually the combination of different gases in contact with a mixture of different liquids. So both the liquids have different composition, and both the gases have also different compositions. So in order to describe a hydrostatic system, again we need to write an equation of state for the systems. So basically the state variable what we are using and we have in thermodynamics are three, that is the pressure, volume and temperature. That could be written to describe any equilibrium state of the hydrostatic systems having single phase. So if the systems undergo a transition from one equilibrium state to another equilibrium state, of course there will be some change or transition in the coordinates or variable as well. Say for example, if initially PVT has different value and the system has been the systems undergoing transition from that equilibrium state to another equilibrium state, then the P, V and T, all of the three will get some new values, and that will be a new equilibrium state. We are considering some simple cases. If we consider that if there is a systems in equilibrium having volume V, and it is going to undergo, and it is undergoing a transition, so there will be some sort of change in the volume, that is called as dV, that is actually the small change in volume. In the same way, there will be some macroscopic behavior of dV and dP as well. If you want to write the equation of states, normally in equation of state we know that two of these state variables are independent while the third one is dependent. So if you want to write volume, that is the function of temperature and pressure, that it could be written as a V is equal to V into TOP. So there will be some sort of infinitesimal change from one equilibrium state to another equilibrium states, and that change could be described with the help of dV, dP and dt. As I already mentioned, that when there is transition from one equilibrium state to another equilibrium state, then accordingly the state variable will change, and the change in the state variable could be represented, the infinitesimal change in the state variable could be represented by dV, dP and dt. So the differential of the volume dV could be written as a based on the fundamental theorem from the differential calculus. So the change in the volume could be written the change in the volume with respect to temperature when the pressure is kept constant. That is actually the first part, and the second part is that the change in the volume with respect to the pressure when temperature is constant. These are actually the two combinations of change that gives us the change in volume. But if we see both of these quantity on the right side of this equation, the first one and the second one, that have a particular physical meaning and are very and possess interesting meaning or physical interpretation in thermodynamics as well as in physics. So here in this case we see this is actually the first thing what we want to know is the first part of this. So we know that the average coefficient of volume expansion is actually the ratio of the change of volume per unit volume and the change of temperature. That is actually, so in this case we consider to be the pressure as a constant quantity. So when we reduce the difference of temperature, so it will have an infinitesimal change. So similarly, if there is infinitesimal change in the temperature, then the resulting change in the volume will be also infinitesimal, and that will lead to the infinitesimal differential coefficient of the volume expansion, which could also be represented by volume expansivity, that is called as beta. So beta is equal to 1 over V, change in the volume with respect to temperature when the pressure is kept constant. So this has an interesting physical meaning, and that is called as volume expansivity. The beta value is always positive only for some cases, just like water that has anomalous behavior of water and some ordinary rubber at room temperature. If we consider the water, if we increase the temperature from 0 degrees centigrade 0 to 4 degree centigrade, then it contracts, and in the same way if we increase the temperature of ordinary rubber, it also contracts with increase in temperature at room temperature. The other part of the equation what we want to know here in this part of the equation, and we want to know the physical interpretation of this other part, that could be easily understandable from the average bulk modulus. If we want to know the definition of average bulk modulus, that is equal to the negative of change of pressure with respect to the change in volume per unit volume. So here normally this is our experience, that if we increase the pressure, then there will be decrease in volume if we keep the temperature constant. Therefore the minus sign in this equation has been introduced to make the value of bulk modulus a positive number. Similarly, if you want to make the changes infinitesimally small, so if we consider the pressure to be infinitesimally small pressure, the resulting change in the volume will be also infinitesimally small volume will be produced, and that will create differential. The resulting bulk modulus will be called as a differential bulk modulus, because all the changes are infinitesimal. So that could be represented because again we want to elaborate that here the temperature is kept constant, so the resulting value is called as a isothermal bulk modulus. That could be represented by B is equal to minus V, change in pressure with respect to volume when the temperature is kept constant. If we consider the reciprocal of the bulk modulus, that is interesting physical property which is called as isothermal compressibility, that could be represented by a Greek letter kappa and measured in Pascal inverse. So kappa could be written as that is equal to minus 1 over V, change in volume with respect to pressure when the temperature is constant. So if we consider the physical property, that is the isothermal compressibility, that is actually slightly vary with temperature for the case of solids and liquids. So normally for very small change, it is considered to be a constant quantity. So the other thing is that is actually the explanation of both part of this equation. This is the differential change in the volume equation of change in the volume with respect to temperature when pressure is constant, and that is the change in the volume with respect to pressure when temperature is constant. One describe the volume expansivity, that is actually a physical, that has a physical meaning, and the other describe the isothermal compressibility, and that both have a very interesting physical meaning. So the next part of this lecture is about the mathematical theorem that could be derived from the partial differential calculus. Again we need to know that if we want to describe any equilibrium state for a thermodynamic equilibrium systems, so we want to use the state variables, and the state variables describe the properties of the system for that particular equilibrium state. If we generalize the case and we represent the state variable in a very general way, not PVT at the end, maybe we can specialize, we can consider only PVT, but if we consider the equation to be very general, so we can consider it a three variable just like x, y and z. So consider that f is a functional possess a functional relationship among the three coordinates, that is f into x, y and z, that is equal to 0. Again we want to elaborate that if we are going to develop a state equation, two among the three variable will be independent while the third one will be dependent variables. Here if we consider that when we consider x coordinate, that is actually the function of y and z, then the change in x could be written by the differential from the partial differential calculus. That will be actually dx is equal to change in the x with respect to y when z is constant into dy, and in the same way change in the x with respect to z when y is constant. So if we consider the y as a function of x and z, then it will be like that that dy will be equal to curly y divided by curly x into z dx plus curly y divided by curly z into x dz. That is actually the change in the volume. So what we want to do, we want to put the value, this value dy, here in this equation, in the first equation. So what will the equation will be modified because we want to solve this first equation. So in the next slide we want to put dy, the value of dy over here, so and then simplify it. So let's see, here we can say I have just put the dx is equal to that was actually the change in the x with respect to y, and when z was constant I just put the value of dy over here from this equation. As I told you before, from this equation we put the value of dy at this place. So what happened, this is actually the part of dy, and this is again the same part of that dx equation. So then in the next steps this value will be multiplied with this part, and in the same way this value will be multiplied with this part. So it will be very easy. In this part is change in the x with respect to y when z is constant, similarly change in the y with respect to x when z is constant, and in the same way we take the dz constant. So this will be multiplied with this quantity, that will be change in the x with respect to y when z is constant, and change in the y with respect to z when x is constant. And similarly the third part of that equation is that change in x with respect to z when y is constant. So among these three, 1, 2, this will be multiplied with each other. So this will be actually a single value, but anyhow that has a dz values, and this, so we can make the common, we can make the dz value common, so we can have these equations. So if we see this equation is very interesting. If we consider that this system could be applied for a state variable, as I told you in the beginning of the lecture, for any particular state variables we have two of these state variables, or maybe the coordinate that are considered to have independent values, where the third one is dependent values. Here in this equation we are putting some values. In this case we have two variables, that describe the change. One is the dx here, and the second one is the dz, because we have eliminated the value dy. So two among the three variables are independent, while the third one is dependent. So we consider different case study. Here the first case is that when dz is equal to 0 and dx is not equal to 0, what will happen? If we consider that dz is equal to 0 and put in this equation, what will happen? This part of this equation will become equal to 0, and if this dx has any particular value, so this equation will have some value over here and some value over here. So if after putting these two value, the resultant equation will be like that this part of this equation will vanish because of the dz value, and we will have only this value. So this will cancel with this one. What we will get, we will get an equation like this: change in x with respect to y when z is constant, and similarly change in y with respect to x when z is constant, that will become equal to 0. And in the same way, if we divide both cases by change in y with respect to x when z is constant, we will have this equation. It's very simple. We consider another case, and another case is that if we consider the value of dx is equal to 0 and dz is not equal to 0, what will happen? The resultant equation will be like that if dx is equal to 0, this part of the equation will become equal to 0, because 0 multiplied by anything leads to 0 values. So similarly this part of this equation will become also 0. The dz will have value like this, that this part of the equation will become equal to 0 because the resultant value are equal to 0. And then we can simplify this part. Maybe we can take one part to the other side of the equation and then simplify it, and this simplification is over here. Okay, when dz is equal to 0, we have these equations. So it will be like that, the value of dz will cancel with each other. So here we can place this value over here to the right side of the equation. It is actually positive. When it moved to the right side, it becomes negative. So the equation is like that. It gives a new form, it achieved a new form. So similarly, if you want to further modify it, what you want to do, we can divide both sides by changing x with respect to z when y is constant. So what will happen over here? We will get -1 because it will cancel with each other. The numerator and denominator will cancel with each other, and at the end here we will get change in x with respect to y when z is constant, multiply by change in y with respect to z when x is constant, and the third one is that change in z with respect to x when y is constant is equal to -1. So this is the final part of the equation. Now we are going to apply this part of the equation on a particular PVT system to develop the state variable for any particular systems. So if we use the same, and we can consider x, y and z as a PVT, pressure, volume and temperature, what will happen? Just replace the x, y and z by PV and T. So the same equation over here, or maybe you can use this equation over here. So this will be modified into this form. And if we see, we have a physical interpretation of these two values: change in volume with respect to temperature when pressure is constant, and similarly the other physical property, that is the change in volume with respect to pressure when temperature is constant. The first one is called as the beta, that is the volume expansivity, and this is isothermal compressibility. The second one is the isothermal compressibility. So we want to put both the values in this equation, and let's see what will happen. We will have a resultant equation like this. Putting the value of beta and kappa in this equation, we will have a resultant equation like this: change in pressure with respect to temperature when the volume is constant, that is equal to beta divided by kappa. And then normally we know that, just like even in the first part of the lecture we described, if we want to find out change in a variable, so it just like for x it was in case of for x it was for y and z, and similarly here we consider a PVT system, so dP will be equal to change in pressure with respect to temperature when volume is constant, and similarly change in pressure with respect to volume when temperature is constant. So we will put the value over here. So this equation will become very simple by putting this value and this value over here. So dP will become equal to, replace this by beta divided by kappa into dt, that is equal to this value, minus 1 over kV into dV. So if we consider the volume to be a constant quantity, so there will be no change in volume. If we consider the volume to be a constant quantity, so there will be no change in volume. If there is no change in volume, so the value of dV will become equal to 0. So anything multiplied by 0 will lead to a 0 values. So we will have dP divided by dP is equal to beta by kappa into dt. This is the new form of this equation, which has interesting meanings. So if we consider a constant volume, of course we will consider constant volume because we have eliminated the dV part of this equation. So what we will do, there will be some change in temperature from initial to final value, which will lead to change in pressure from initial to final value. So we will integrate this equation. If we integrate this equation from initial to final values, so what will happen? The left side of the equation will become, when we integrate it by differential integrate it, so it will have PF minus PI, that will be equal to beta divided by kappa into dt. Here we have two values, that is beta by kappa divided by kappa. If we consider this value to be a constant quantity, actually it varies, but for very small change in temperature it is considered to be a constant values. If there is very small change in temperature, small change in temperature, maybe 10 degrees centigrade or 15 degrees centigrade, so there is no reasonable change in the value of beta and kappa, and it is considered to be a constant quantity. So this constant will come out from the integration. So we need to integrate only the dt. So what will happen in the next slide, the resultant case will be like that Pf minus Pi is equal to beta divided by K is equal to Tf minus Ti. So this is really a very interesting equation, and we can solve different problems on these equations. And because if you want to find, if we know the initial value of the pressure or temperature, we can find out the final values, because beta and kappa are the constant quantity. The only variable in this case are the initial and final pressure, and similarly the initial and final temperature. So if we know three values among the four, we can easily find out the third value. So this is something about the hydrostatic systems and the theorem differential from differential calculus about the thermodynamics. So I hope we can keep in touch for the next lecture. Thank you very much.